In early 1940, the temperature outside is -40°, your oxygen mask is freezing to your face, and you've got one job. Drop bombs in a factory 5 mi below. Simple, right? You can see the target clearly through the bomb sight. Weather's perfect, no clouds. No enemy fighters harassing you at this exact moment. Just you, gravity, and basic physics. Except nothing about this is basic. The moment you release a 500 lb bomb from 4 miles up, that bomb doesn't drop straight down like a rock into a pond. It inherits every single bit of your aircraft's forward velocity, roughly 180 mph. So while gravity pulls it down at 32 feet per squared, the bomb is simultaneously screaming forward at 264 ft/s. You're not dropping a bomb. You're throwing a ballistic projectile on a parabolic arc, and you need to calculate exactly where that arc intersects with the ground. But here's where it gets ugly. That bomb takes about 40 seconds to fall from 20,000 ft. During those 40 seconds, it travels forward approximately 2 miles. Not straight down, 2 miles forward. So you can't aim at the factory. You have to aim at an invisible point in empty space 2 miles before the factory, release the bomb, and pray your calculations were correct. And we haven't even talked about wind yet. At 20,000 ft, wind speeds can hit 100 mph or more. That wind is pushing your bomb sideways the entire time it's falling. A 30 mph crosswind, which is moderate at that altitude, will push your bomb roughly half a mile off course. The bomber needs to calculate wind speed, wind direction, and how much drift compensation to add. Except he can't measure the wind directly. He has to estimate it based on ground speed, compass heading, and airspeed indicator readings that might be wildly inaccurate because of instrument error. In 1940, bombarders used something called the Sperry Bombsight or earlier Mark 115 models. These were essentially advanced protractors with some gears and mirrors. The bombardier would look through the sight, manually track the target, twist knobs to input airspeed and altitude, make educated guesses about wind, and hope for the best. The best trained bombarders in the U.S. Army Air Corps, practicing over the Nevada desert with unlimited time and perfect conditions, were hitting within 400 ft of their targets only about 50% of the time. 400 ft. That's more than a football field. When your target is a specific factory building that's maybe 200 ft long, a 400 ft margin of error means you're statistically more likely to hit the empty field next to the factory than the factory itself. The British discovered this the hard way during early daylight raids in 1939 and 1940. Bomber Command sent Wellington and Blenheim bombers against German naval targets and industrial sites. Post-ray reconnaissance photos revealed a horror show. Only about 20% of bombs were landing within 5 miles of the intended target. 5 miles. Entire bomb loads were obliterating French farmland, empty forests, and the occasional unlucky village. While the actual German war factories remained untouched, the math was brutally simple. If you needed to destroy a factory, you had to send 30 bombers, each carrying 4,000 lb of bombs, just to ensure maybe 1 or 2 bombs actually hit the building. That's 120,000 lb of explosives, 30 flight crews risking their lives, and astronomical amounts of fuel and resources, all to accomplish what one accurate bomber could theoretically do. The U.S. military looked at these numbers in 1940 and realized they had a catastrophic problem. America wasn't in the war yet, but everyone knew it was coming. The doctrine was clear. Strategic bombing would Germany's ability to make war. But strategic bombing only works if you can actually hit strategic targets. Without a solution, the entire bombing campaign would be nothing more than expensive, deadly, random terrorism from the sky. Someone had already been working on that solution for nearly a decade. Carl Lucas Norden didn't look like a man who would change the course of World War II. Born in 1880 in Semarang, Dutch East Indies-Swiss parents, he was quiet, methodical, and utterly obsessed with precision. His colleagues at the Naval Consulting Board in 1911 described him as the kind of engineer who would spend 3 hours recalculating an equation just to verify the 4th decimal place. Most people found this annoying. The U.S. Navy found it useful. Norden had studied engineering at the Swiss Federal Institute in Zurich before immigrating to the United States in 1904. By 1913, he was working on gyroscopic systems for naval equipment, specifically trying to stabilize gun directors on battleships. When a battleship fires its main guns, the entire ship rocks. When the ship is moving through rough seas, it's pitching and rolling constantly. Hitting a target 10 mi away under those conditions is impossible, unless you have a stable reference point that ignores all that movement. Norden became obsessed with gyroscopes because they offered something almost magical, a spinning mass that maintains its orientation in space regardless of what's happening around it. During World War I, Norden consulted for the Navy on various stabilization projects, but it was after the war that he found his true calling. In 1920, the military was experimenting with dropping bombs from aircraft, a new and wildly inaccurate practice. Army Air Service General Billy Mitchell was out there proving that aircraft could sink battleships. But the accuracy was abysmal. It required multiple aircraft making multiple passes, and even then success was more about quantity than precision. The Navy approached Norden in 1921 with a question. Could gyroscopes solve the bombing accuracy problem? Norden spent 6 months studying the issue and came back with an answer that shocked everyone. Not only could gyroscopes solve it, he could build a bombsight so accurate that a bombardier could drop a bomb into a pickle-barrel from 20,000 ft in a pickle-barrel 3 ft wide. Most engineers at the Naval Research Laboratory thought Norden had lost his mind. The best bombsights in 1921 couldn't hit within a 4-mile. Norden was promising 3-foot accuracy. That's not an incremental improvement. That's claiming you can perform miracles. But Norden wasn't making empty promises. He'd done the math, and more importantly, he understood something about bombing that everyone else had missed. The problem wasn't the bomb. The problem was the bombarder's reference frame. Every bombsight up to that point required the bombardier to manually track the target while the aircraft was moving, calculate all the variables in his head or with basic mechanical computers, and then guess when to release. The bombarder was the unstable element. Human reaction time, human error, human limitations. These were the real obstacles. What if you could remove the human from the equation? Not entirely, but partially. What if the bombsight itself could maintain a perfectly stable reference to the ground, automatically calculate the bomb's trajectory, and tell the bombarder exactly when to release? The bombardier would just need to keep the crosshairs on target. The machine would do everything else. In 1923, Norden founded Carl L. Norden, Inc. in a small workshop in Brooklyn, New York. He took a Navy contract worth $75,000, about $1.3 million in today's money, and disappeared into his workshop with one engineer assistant, Theodore Barr. For the next several years, almost nobody heard from him. He wasn't interested in progress reports or prototypes or impressing military brass. He was interested in perfection. The Navy got nervous. $75,000 was serious money, and Norden wasn't showing them anything. But in 1927, he finally emerged with a working prototype designated the Mark Geffen. It looked like a complex mechanical brain mounted on a tripod, gears, mirrors, gyroscopes, all enclosed in metal housing. Norden transported it to a test range and demonstrated it personally. The results were classified immediately, but word leaked through military channels. Norden had actually done it. His bombsight was hitting targets with accuracy nobody thought possible. The pickle-barrel wasn't just marketing. It was a promise Carl Norden intended to keep, and he was willing to spend the rest of his life perfecting the machine that would make it reality. But Norden's prototype revealed an even uglier truth about the bombing problem. Even if you could calculate the perfect release point, accounting for altitude, airspeed, wind drift, and ballistic trajectory, all of that math became worthless garbage the instant the aircraft moved. And aircraft never stopped moving. Stand in an open field on a calm day and you're standing on a stable platform. North stays north. The horizon stays level. If you point at a distant tree, your finger keeps pointing at that tree unless you move it. Now stand on the deck of a ship in rough seas. North still stays north, but you're pitching forward and back, rolling side to side. And if the ship is turning, you're yawing left or right. Point at that same distant tree and your finger is drawing wild circles in the air, even though you're trying to hold it steady. A bomber at 20,000 FT's that ship, except worse. Much worse. Aircraft movement breaks down into 3 axes of rotation, and every single one of them destroys your bombing solution. Pitch is the nose going up or down. Roll is the aircraft tilting left or right on its long axis. Yaw is the nose swinging left or right while the wings stay level. In a perfectly trimmed aircraft flying through absolutely calm air with an expert pilot, you might have 2 or 3 seconds of stability before turbulence or a tiny control input changes something. Here's what that movement does to your calculations. You're tracking a factory through your bombsight and you've spent 20 seconds getting everything perfect. Airspeed 180 mph, altitude 20,000 ft, wind correction 15 to left. You've calculated that you need to release in exactly 12 seconds when the target reaches the crosshairs. Perfect. Then a gust of wind hits the bomber. The nose pitches up 3 deg. 3D doesn't sound like much. It's barely noticeable inside the aircraft. But 3 degrees of pitch at 20,000 FT means your bomb trajectory just changed by over 1,000 FT. Your bomb, which was going to hit the factory, will now land in their residential neighborhood a quarter-mile beyond it. And you don't have time to recalculate because now the aircraft is rolling 2 degrees to the right as the pilot corrects, which adds another 600 FTO for horizontally, and you still have 11 seconds until release, during which the aircraft will move at least a dozen more times. The bombarders in 1940 weren't stupid. They understood the math. The problem was that the math required a stable firing platform, and no such platform existed. The Sperry Bombsight tried to compensate by using a gyroscope to keep the optical system stable, but it was a single-axis gyroscope that only corrected for one type of movement at a time. If the aircraft was pitching and rolling simultaneously, which was always, the Sperry could only fix one problem while ignoring the other. Experienced bombarders developed a feel for it. They'd watch the target drift in the sight and make intuitive corrections, releasing early or late based on gut instinct. The best bombarders, guys like Major Lewis Carrington, who trained at Lowry Field in Colorado, could feel the aircraft's movement through their whole body and compensate subconsciously. But this wasn't a skill you could teach to thousands of young men being rushed through training. This was an art form, and art doesn't win wars. Repeatable mechanical precision wins wars. The British tried a different approach. If you can't hit accurately, hit everything. Bomber Command shifted to nighttime area bombing in 1940, dropping thousands of tons of explosives on entire German cities rather than specific factories. It was effective at destroying German morale and industrial capacity, but it was also slaughter. Tens of thousands of civilians died because British bomb sites couldn't compensate for aircraft movement well enough to hit a factory without leveling the surrounding neighborhood. American military doctrine rejected area bombing. The U.S. wanted precision daylight bombing, hitting factories, oil refineries, rail yards, and submarine pens while leaving civilian areas intact. This wasn't purely humanitarian. Military planners believed that precision targeting would Germany's war machine faster and with fewer resources than carpet bombing entire cities. But precision required solving the movement problem. And in 1940, nobody had solved it except possibly one obsessive Swiss engineer working in a Brooklyn warehouse. Norden's breakthrough came from understanding a physical principle that had been known since the 1850s, but never properly weaponized: gyroscopic rigidity in space. Take a bicycle wheel, spin it fast, and try to tilt it. The wheel resists. It wants to maintain its orientation. Spin it faster, and their resistance gets stronger. This isn't magic or electromagnetic force. It's conservation of angular momentum. One of the fundamental laws of physics, a gyroscope is just a wheel spinning inside a frame. But that frame is special. It's called a gimbal, and it allows the wheel to rotate freely in any direction while the wheel itself keeps spinning in its original plane. You can pick up a gyroscope, flip it upside down, shake it, spin it around, and that wheel inside refuses to change its orientation. It's locked onto a reference axis in space, and it's staying there no matter what you do to the frame around it. Here's why that's extraordinary for bombing. If you mount a gyroscope in an aircraft and spin it up before takeoff, that gyroscope is now locked onto Earth's gravitational vertical. The aircraft can pitch, roll, and yaw all at once. The gyroscope doesn't care. It maintains its original orientation relative to the ground, not relative to the aircraft. It's like having a tiny piece of stable ground floating inside your unstable bomber. Norden realized this solved everything. If the bombsight's optical system was linked to a gyroscope instead of being fixed to the aircraft frame, the sight would automatically compensate for all aircraft movement. When the bomber pitched up, the gyroscope would stay level and the sight would adjust, keeping the bombarder's view locked onto the actual ground below, instead of tilting with the aircraft nose. When the aircraft rolled, same thing, automatic correction. The bombardier wouldn't even know the aircraft was moving because from his perspective, staring through the bomb sight, the ground stayed perfectly stable. But Norden needed more than one gyroscope. Aircraft move in 3 dimensions, and a single gyroscope can only maintain reference in one plane. The Mark 115 Norden bombsight, which entered final development in 1931, used a 3-axis gyroscope system, 3 separate spinning wheels, each mounted in its own gimbal system, each maintaining reference for a different axis of movement. The primary gyroscope handled pitch and roll. It spun at approximately 8,000 revolutions per minute, powered by a vacuum pump that sucked air through the system to spin the rotor. This wasn't a small wheel. The rotor was about 4 in diameter and made of hardened steel, precisely balanced to eliminate any wobble. At 8,000 RPM, that rotor was storing enormous angular momentum, making it almost impossible to deflect from its reference orientation. The second gyroscope handled directional stability, maintaining the sight's heading reference even as the aircraft yawed during turns or in crosswinds. The third gyroscope was actually part of the automatic pilot system that Norden integrated into later models, allowing the Bombsight to physically control the aircraft during the bombing run. But that was still years away in 1931. What made Norden's system brilliant wasn't just using gyroscopes. The Sperry Bombsight already did that. What made it brilliant was how Norden connected the gyroscope reference to the sighting mechanism and the bombing computer. The gyroscope didn't just stabilize the view. It actively fed data into a mechanical computer that calculated trajectory based on the gyroscope's stable reference rather than the aircraft's unstable reference. Think of it like this. Previous bombsights were trying to do calculus while riding a roller coaster. The bombardier was inside the moving reference frame, trying to calculate trajectories while being thrown around. Norden's sight stepped outside that reference frame. The gyroscope created a stable platform that existed independently of the aircraft's chaos, and all calculations happened relative to that stable platform. The gyroscope refused to lie about which way was down, which way was forward, and where the aircraft actually was in space, and because it refused to lie, the Norden sight could tell the truth about when to drop the bombs. But a gyroscope maintaining spatial reference is only half the battle. Norden had to translate that stable reference into actual bombing accuracy, and that required building one of the most complex mechanical computers ever created in the 1930s. The complete Mark 115 bombsight weighed about 50 lb and contained over 2,000 precision parts, many machined to tolerances of 110,000th of an inch. Each component had to work in temperatures ranging from 40 to plus 120 degree or F at altitudes, where air pressure was 1/3 of sea level, while subjected to constant vibration from 4 massive radial engines. The system started with power generation. The gyroscopes needed to spin at 8,000 RPM continuously, which required a dedicated vacuum pump mounted in the aircraft fuselage. This was an Asmol pump. It pulled 7.5 cubic feet of air per minute through the gyroscope housings using the Venturi effect to spin the rotors. The pump itself was driven by the aircraft's electrical system, pulling about 5 amps at 28 volts. Bombarders had to switch it on 15 minutes before the bombing run to let the gyroscopes reach full speed and stabilize. If the pump failed or the gyroscopes didn't reach proper RPM, the entire sight was useless. Once the gyroscopes were spinning, they created what Norden called the stable vertical, an artificial horizon that ignored everything the aircraft was doing. The bombardier's telescope was physically mounted on a gimbal system, connected to the primary gyroscope through a series of gears and linkages. When the aircraft pitched up 5 degrees, the gyroscope stayed level and the gears automatically tilted the telescope down 5 degrees relative to the aircraft, keeping the bombardier's view pointed at the same spot on the ground. This stabilization happened in real time through what engineers today would call a mechanical feedback loop. The gyroscope detected deviation from level. That deviation moved a gear. The gear adjusted the telescope position. The telescope stayed locked on target. All of this occurred mechanically with no electronics. No computers in the modern sense, just precisely machined metal parts transferring rotational force through the system. But stabilization was only the first function. The sight also had to calculate the release point, and this is where Norden's mechanical genius really showed. The bombardier input airspeed using a dial on the left side of the sight. He input altitude using another dial. The sight measured ground speed automatically by tracking how fast landmarks moved past the crosshairs, essentially doing calculus mechanically. A disc and drum computer inside the sight took all these inputs and continuously calculated the bomb's trajectory. This mechanical computer is differential gears, cams, and circular slide rules machined into bronze discs. As the bombarder tracked the target, these components rotated against each other, solving the ballistic equations physically. The computer calculated trail, how far the bomb would travel forward during its fall. It calculated drift, how far wind would push the bomb sideways. It calculated range, the actual ground distance to target, after accounting for altitude and approach angle. All of these calculations fed into what Norden called the synchronous bombing method. The bombardier kept the crosshairs on target, while the site's computer continuously calculated the perfect release point. When the aircraft reached that point in space, not when the target appeared at a certain position in the site, but when the aircraft was at the exact three-dimensional coordinates where releasing the bomb would result in a hit. An electrical circuit completed and the bombarder pressed the release. The beauty of the system was that it worked automatically. The gyroscopes compensated for movement. The mechanical computer solved the math. The bombarder just had to keep the crosshairs steady on target and trust the machine. In theory, a moderately trained bombardier using a Norden sight should achieve the same accuracy as an expert using any other bomb sight. In theory, testing began in earnest in 1933 at the Naval Proving Ground near Dahlgren, Virginia on the Chesapeake Bay. Norden himself supervised the trials, flying in Navy observation aircraft while bombarders dropped practice bombs on target rafts floating in the bay. The early results were classified immediately, but internal Navy documents from 1934 show something remarkable. Bombardiers with minimal training were consistently placing bombs within 75 ft of the target from 10,000. At 75 ft, that was better than the best bombarders in the world could achieve with any other sight. And these were average recruits on their first attempts. The pickle-barrel claim wasn't quite literal. Nobody was actually dropping bombs into 3-foot barrels from 4 miles up. But 75 ft was close enough that military planners started doing new math. If one bomber with a Norden sight could hit a specific factory building, you didn't need 30 bombers anymore. You needed 3, maybe 5 for redundancy. That was a force multiplier that changed strategic bombing from a theoretical concept into a practical war-winning strategy. The Army Air Corps ordered their first batch of Norden sights in 1933, but with conditions that seemed paranoid, even by military standards. Each sight was assigned a serial number. Each sight required 2 armed guards whenever it moved from one location to another. Bombarders had to swear a formal oath, not just a general security clearance, but a specific oath about the Norden sight, promising never to discuss its mechanisms or capabilities with anyone lacking proper authorization. Violating that oath was considered treason, punishable by up to 20 years in prison and a $20,000 fine. When bombarders trained at Lowry Field in Colorado or at Midland Army Airfield in Texas, the Norden sights were stored in special vaults with combination locks. Only 3 people on each base knew the combinations before each training flight. Guards removed the sight from the vault, accompanied it to the aircraft, watched the bombardier install it, and remained with the aircraft until the flight ended and the sight was returned to the vault. If an aircraft carrying a Norden sight experienced mechanical problems away from base, armed guards were dispatched immediately to secure the device. This wasn't security theater. The Norden sight represented nearly 15 years of engineering development and somewhere between 1.5 and 2 billion in total program costs. That's in 1940s dollars equivalent to early 30 billion today. Each individual sight cost approximately $8,000 to manufacture, more expensive than the aircraft carrying it. A B-17 bomber cost around $200,000, but that included 4 engines, defensive guns, and space for a 10-man crew. The Norden sight was 50 lb of gears and gyroscopes that cost $8,000. By 1940, Norden's company was producing about 50 sights per month in their Brooklyn facility. That number climbed to 200 per month by 1942, and eventually topped 600 per month by 1944. Each sight required individual hand fitting and calibration. Gears had to mesh within tolerances measured in microns. Gyroscope bearings had to be perfectly balanced. The optical system had to be aligned to exacting standards. This wasn't mass production in the modern sense. It was precision instrument manufacturing scaled up to wartime demand. The security extended to combat operations. Before every mission over Europe, bombarders signed out their assigned Norden sight and signed it back in after landing. If a bomber was shot down, the bombardier was instructed to destroy the sight before bailing out. Special thermite charges were installed for this purpose. Several bombarders died trying to destroy their sights rather than let them fall into German hands. The Germans knew about the Norden, knew it was drastically superior to their own Lautern-Rohr 7 bomb sight, and wanted one desperately for reverse engineering. Carl Norden himself became a ghost. He refused interviews, avoided publicity, and continued refining the sight throughout the war. The man who promised pickle-barrel accuracy had delivered something close to it. And now the question was whether it would actually work when people were shooting back. The first combat test came on August 17, 1942, when 12 B-17 bombers from the 97th Bombardment Group attacked the railroad marshalling yards at Rouen-Sotteville in occupied France. Each bomber carried a Norden sight. Each bombardier had trained for months on the device. The mission briefing promised surgical precision. Hit the rail yards. Avoid the civilian housing 400 yards away. Proved that American daylight precision bombing could work. The raid was considered a success. Post-strike reconnaissance photos showed significant damage to the rail infrastructure. The military press releases celebrated it as validation of the Norden site's capabilities. General Ira Eaker called it proof that precision bombing would win the war. But the actual after-action reports declassified decades later told a more complicated story. Of the 36,900 lb of bombs dropped that day, only about 50% landed within 1,000 ft of the aiming point, 50% within 1,000 ft. Not pickle barrels, not even small buildings, a quarter-mile circle. And that was under nearly ideal conditions. Light flak, no fighter opposition, clear weather, minimal combat stress. As the war progressed and missions pushed deeper into Germany, reality diverged sharply from the testing range results. The 8th Air Force maintained meticulous bombing records throughout the war. By 1943, they were flying hundreds of sorties per month against German industrial targets, and the statistics were humbling. Under combat conditions with enemy fighters, heavy flak, and experienced crews, average accuracy was approximately 300 to 400 ft circular error probable, meaning half of all bombs landed within 300 to 400 ft of where the bombardier aimed. That's still impressive compared to 1940 standards, but it's nowhere near the 75 ft accuracy achieved during peacetime testing. Several factors explained the degradation. First was flak. German anti-aircraft batteries fired proximity-fused shells that detonated near bombers, creating shrapnel clouds. When jagged metal is ripping through your aircraft at 20,000 ft, punching holes in hydraulic lines and fuel tanks, killing the navigator next to you, maintaining concentration on the Norden site's crosshairs becomes difficult. Bombarders reported that during heavy flak, their hands shook so badly they couldn't keep the sight steady. The Norden's gyroscopes compensated for aircraft movement, but they couldn't compensate for human terror. Fighter attacks created worse problems. When Messerschmitt Bf-109s or Fäkalf FW-190s came screaming through the formation at 400 mm, firing 20mm cannons, bombers had to break formation and maneuver violently. Evasive action meant banking hard, diving, climbing movements that overwhelmed even the Norden stabilization systems. Many bombarders simply salvoed their bombs and focused on survival rather than accuracy. Weather was the silent killer of precision. The testing at Chesapeake Bay happened in clear visibility over Germany. Cloud cover frequently obscured targets. Even with the Norden sight, you can't hit what you can't see. By 1944, the 8th Air Force was using radar-assisted bombing techniques like H-2X for missions with poor visibility, essentially abandoning the Norden and dropping bombs based on radar images. Accuracy plummeted to over 1,000 ft circular error, sometimes worse. The Pacific Theater presented different challenges against Japanese shipping and island targets. The Norden worked better because ships and concrete bunkers were easier to identify and track than camouflaged German factories in urban areas. The 5th Air Force operating B-17s and later B-29s in the Pacific reported somewhat better accuracy, averaging 250 to 300 ft against major targets. The mission against the Mitsubishi aircraft plant in Nagoya on December 13, 1944, put 28% of bomb within 500 ft of the aiming point. Considered excellent under combat conditions, but even that success highlights the gap between promise and reality. 28% within 500 ft meant 72% of bombs missed by more than 500 ft. The Norden had made bombing dramatically more accurate than 1940 standards, but it hadn't delivered miracles. The war ended with mixed assessments of the Norden site. Strategic bombing surveys conducted in 1945 concluded that only about 20% of bombs dropped by the 8th Air Force hit within 1,000 ft of their targets. The dream of pickle-barrel accuracy never materialized in combat, and some military analysts argued the massive investment in the Norden program had been wasteful. Carl Norden himself died in 1965, largely forgotten by the public, his name absent from most World War II histories. But dismissing the Norden as a failure misses the fundamental revolution it represented. Before Norden, bombarders aimed through crude optical sights and guessed. After Norden, they used gyroscopically stabilized instruments that automatically computed ballistic trajectories. The technology didn't deliver perfection, but it dragged bombing accuracy from medieval guesswork into the realm of engineering science. More importantly, the principles Norden pioneered: gyroscopic stabilization, inertial reference frames, and automated trajectory calculation, became the foundation of every precision guidance system developed afterward. The direct lineage runs through the Air Force's research programs in the 1950s. Engineers working on early cruise missiles faced the same problem Norden had confronted. How do you guide a weapon to a target when the weapon itself is moving through three-dimensional space? The answer was inertial navigation systems, descendants of Norden's gyroscope assemblies. The MGM-13 Mace cruise missile deployed in 1959 used 3 gyroscopes to maintain spatial reference exactly as the Norden sight had. Except now the gyroscopes were controlling flight surfaces rather than bombsight optics. By the 1960s, gyroscopic inertial navigation systems were standard equipment on strategic bombers, ballistic missiles, and even commercial aircraft. The Boeing 747, first flown in 1969, used triple redundant inertial navigation units to cross oceans without ground-based navigation aids. Each unit contained 3 gyroscopes maintaining reference on 3 axes: pitch, roll, and yaw. The basic architecture was Carl Norden's 3-axis stabilization system, miniaturized and enhanced with electronics instead of mechanical computers. Modern weapons have evolved beyond mechanical gyroscopes into ring laser gyroscopes and fiber optic gyroscopes, but the principle remains identical. The AGM-86 cruise missile, deployed in the 1980s and still in service today, uses inertial navigation to fly hundreds of miles to targets with accuracy measured in feet. The Tomahawk cruise missile combines inertial navigation with GPS and terrain-matching radar. But when GPS is jammed or unavailable, it falls back on pure inertial guidance, trusting gyroscopes to maintain spatial reference, just as Norden's bombarders did over Europe. Drone technology represents perhaps the purest expression of Norden's vision. The MQ-9 Reaper and other unmanned combat aircraft use inertial measurement, units containing accelerometers and gyroscopes that provide continuous data about the aircraft's orientation and movement. This data feeds into flight computers that stabilize the aircraft and calculate weapon trajectories automatically. The human operator designates the target. The machine handles everything else. That was exactly what Norden tried to achieve, removing human error from the bombing equation by letting stabilized instruments handle the calculations. Even smartphones contain Norden's legacy. The gyroscope chip in your phone, measuring a few millimeters across, detects rotational movement using vibrating silicon structures instead of spinning wheels. But it's performing the same function Norden's foreign steel rotor performed in 1940, maintaining a reference frame for calculating position and orientation in 3-dimensional space. Carl Norden never got his pickle-barrel, but he got something more important. He proved that gyroscopic stabilization could solve previously unsolvable problems in guidance and navigation. Every precision weapon, every autopilot system, every inertial navigation unit used today traces its conceptual lineage back to a Swiss engineer who spent 15 years obsessing over spinning wheels and gimbal frames in a Brooklyn workshop. The specific hardware is obsolete, but the principles are immortal.